No. Now, when we first have something called a web page, okay, people think that, oh, we need to have a chart so that you know which page is linked to which page. So in those ancient websites, we always have a thing called a sitemap. When you click on sitemap, you will see that this is the home page, this is the products page, this is product 1, product 2, to show you the link. Now imagine you have a website and you want to show a sitemap, then your sitemap will be so forget about it, but that is actually how the internet works, right? You know that is actually a tree. You have a home page most of the time, and you will link to different pages, and you go on and link to different pages. Okay, we call it a sitemap. Now I'm curious. Do people still use sitemap now? Well, people do ask this question, so you can, but I don't think anyone have any examples. Well, Google still have a sitemap generator that allows you to generate a sitemap. Okay, so supposedly, you can still create a sitemap.
So your team is about to start a new website redesign project, and you've been tasked with the discovery and planning phase. You need to assess the existing architecture of your client's website, and your new client has limited knowledge on what's contained in their website inventory. The story's always the same, isn't it? A company builds a website, and after years of updates to their website architecture, the site becomes very unorganized and impossible to decipher. The client has no idea how many pages, images, links, and exactly how many errors, missing files, and bad links have compromised their once pristine website build. Dino Mapper is an awesome new service that takes the pain away from planning your next website build. How? It's simple. Just enter a URL and click Create Sitemap. Then presto, Dino Mapper will inventory your website and create an interactive visual sitemap that displays.
So that means nowadays it's not for visitors. You create a site so large that you don't even know how your site looks. Okay, so now you can create a sitemap, so you realize, oh, there's a whole section of site that we have never used. Or, oh, this is a whole lot of missing links. Okay, so now, you see, sitemap is still useful. Okay, so it's a tree, obviously, right? You look at it, it's a tree. Home is the root node. So that's why if you use a web server, it's called a web root. Okay, because it's a tree. Okay, now so let's go on. Okay, GUI is also a tree. In your Android or Windows, you have a panel, and then inside the panel there are buttons, and inside the buttons there are some text and then something like that, and it is also a tree. Okay, in next year you will have a chance to do some GUI, and you know that it is a tree. And some naturally hierarchical data, okay, such as organization structure, family tree, or any web pages. Okay, so here you look at the HTML code, and if you look at the elements here, now obviously you see that this is also a tree, right? All the text of HTML text, for those who don't know, this is HTML, and all those things are also a tree. Okay, you will notice that it's a tree structure because I have a certain last space, and then I have to go into smaller and smaller spaces. Okay, so this is actually how we model many things. Now, so trees are actually everywhere. It's more important than you think. Okay, every day you are actually using trees, and I hope you convince you that. Now, to operate on a tree, you need some very weird operations. Traverse. Now, if you remember from linked list, traverse means to go from the beginning of a linked list to the end. But now I have a tree. So to traverse means I go through the whole tree. Now, the tree doesn't offer a unique path. Okay? So if I look at this tree, I need to go through all the elements. I don't have a single path. So traverse is not easy. Now, not to mention this is a graph, not a tree. If I traverse, I will be A, B, C, E, D, B, C, E, D, B, C. Okay. So you get the idea. When you have a very complicated data structure, traversal becomes hard. Okay? So it's called traverse. You need to search. Again, you have many paths and you want to find one node. How do I search? Which way is the fastest? I need to add, I need to remove, I need to get children, I need to get parents. Okay? So basically, you also have different operations to do. Now, to implement a tree, obviously we use a tree data structure. So a tree ADT is essentially the same as a tree data structure. Now, a tree as a data structure is somewhat magical. Now, I hate to use this word, but actually, tree as a data structure can actually represent many other ADTs. For instance, just now I say ordered set and ordered dictionary. They can actually be represented by a tree. Now, why is that? Okay, for those who have never seen a tree before, you may realize, how can I use a tree to represent a dictionary? Okay, and why should we do that? Okay, so in next chapter, we are actually heading to the next chapter directly. We are going to see how actually trees are used. Now, I will give you a warning. The moment we step in trees, the course will lose half the people. Okay, trees is hard. Okay, so we are now finally going to a hard topic, trees and grass. Okay, so please pay attention. If you have a friend who just think that I'm doing project, I'm taking a break, I'm waiting for Easter, please, okay, tell him or her. Okay, trees are going to be hard. Now, how hard? So hard that we will only talk about one type of tree called binary tree. Now, what is a binary tree? Now, this is not an ADT. Okay, a binary tree is really a data structure. A binary tree is a data structure tree in which each node have no more than 2 children. Okay, we make sure that you can only split into 2 ways at most every time. So here we have a binary tree. Okay, now a binary tree itself is very useful because binary is very prevalent in our mathematics. We usually have binary operands. Okay, we usually have binary numbers. Okay, so binary tree is very important. Now, may I remind you, as a data structure, binary tree follows the terminology of the tree. Who is the root of the tree? Binary tree. A. Okay. And who are the leaf nodes? D, F. Yes. Okay. So we have the child nodes. A, B, C, D are all child nodes of somebody, and they are leaf nodes. And the height of the tree here is 2. Okay. The first one is 0, 0, 1, 2, and so is the depth. Okay. Now the requirement of binary tree is actually pretty clear, and because this is a data structure, we have C code. Finally, today, suddenly you see C code. Okay. Again, we go back from the abstract level to the implementation level. You look at this. To implement a binary tree in C, we have something like that. We have a structure node, and we have the data inside, value, and we have the left child pointer and the right child pointer. Does it bring some nightmare? Your first left, the list, okay? Now, so as I said just now, right? A linked list is also a tree, right? So a linked list is also only a special case, right? You only have one child, okay? So in this case, you can imagine you can implement linked list. So here, this is a linked list, but also a binary tree, right? It's a faded binary tree. Now, so just like in linked list, the pointer to the root node is the header, and it represents the binary tree in C. Now, the formal definition of binary tree is actually recursive. I have a root, and I have 2 binary subtrees, the left subtree and the right subtree. Okay? So as long as it fulfills the definition, it is a binary tree. Okay? Of course, the left subtree can be null, okay, or one node, or many nodes. But this is the recursive definition of the binary tree. Okay? So what is special about binary tree? As I said just now, even for a tree, any tree, okay, the operations are complicated. How complicated? Here I say binary tree is a complicated data structure. Now in simpler data structure, such as linked lists, arrays, how complicated it is, right? In lab 1 you find it very complicated. Now you realize that it's just, wow, next is not now current equals to next. It's just that, okay? But in binary trees, the operations are very complicated. Now why is that? Because it's ambiguous. What is ambiguous? It means it has many meanings. Okay? Now in a linked list, when I say you insert into the end, that is insert to the end. Now you look at a binary tree. I say add a new node G to the tree. Where do I add it? I can add it to D, E, F, C, B dot, and C. Okay? They are all spaces. Okay? Why? When we add it, what happens? Right? If I now want to delete A, what will happen? Okay. Now, yeah, it's a lot of trouble, right? So in binary trees, the operations are complicated because we do not know what to do. Okay? They are not complicated in that they are difficult to implement. They are complicated because there are many possible choices, and you need to choose the right one for the right applications. Okay? Now, so suddenly your data structure has operations that is application dependent. We call it a context. Now, give you an example. Traversal. Now, to traverse a tree means to visit all nodes to the tree, right? There are many ways to traverse a tree. I will introduce you to one by one. Say now you have this tree. Now, if I want to go through all the nodes, the very first way I can do it is what we call in-order traversal. Now, what is in-order traversal? Here, I have this recursive function. I will traverse in order, then I will recursively look at the left child, and then I will print out myself. Then I will recursively look at the right child. Now, what is the output of this? Now, imagine now, in order means I will look at the left child first, and then look at myself, and then look at the right child. Right? This is the order. So I go into the node 50, but I don't look at 50 first. I go and look at the left child first, right?
20 first.
Then I go at 30. But then, I go and look at 30 first. I look at the left child first, right?
Yes.
So I look at 20. Okay, so the first node that I visit is actually 20. And then, I look at myself, right? Then it is 30. Okay. Now, in this case, I can look at the right child, 40. Okay, so this subtree is done. And then, after this subtree is done, the left child to him is done, right? So I look at 50, and I look at 60. Okay, so the order is actually 20, 30, 40, 50, 60. Okay? This is what we call in-order traversal. Okay? Notice that I have gone through the whole tree once, without repeat. That's very important, right? If I do other methods, say I create a function, 50, 30, 20, 30, 40, 30, 50, 60, oh, then I'm in trouble. So I need to know, okay, who I go first, okay? So this is in order. The result, 20, 30, 40, 50, 60. Now, the subtree process order is left, root, and right. Now, when you look at this, it is helpful to look at this diagram. Okay? Because for a binary tree, the definition is recursive. So it's actually easier to imagine the binary tree is only three things. The left tree, myself, the root, and the right tree. Okay? So that you know that there's fixed number of things you need to do every time. Right? This is free. Right? If you look at a binary tree like this, 1, 2, 3, 4, 5, 6. Every time is different, right? So it's hard to abstract, okay? So look at this, okay? 1, 2, 3. So I can also do an in-order traversal. A, I do the left child first, so it's B. But actually, I also have the left child, it's C. So if I do an in-order traversal, it's CBA. Okay? Okay, so this order. Now, this is one way to do a traversal. Let's do another way. Pre-order traversal. I will take care of myself first, and then I will do the left child, and then I will do the right child. Perfectly fitted, right? So here, if I look at this, I will do myself first. 50, then 30, then left child, 20, then 40. So this left tree is completely done, right? So ultimately 60. So if I do a pre-order traversal, it will be 50, 30, 20, 40, 60. A different order, right? I deliberately use an order because the in-order traversal, you see that the numbers are in order. Okay? In the pre-order traversal, you see the numbers are now mixed up, right? The root will come first. Now, obviously, you will notice the next possibility is post-order traversal. In post-order traversal, we will take care about the left child first, and then the right child, and then myself. Okay? Now, the order will become, sorry, I forgot again. Left child first, okay. Okay, left child first, 50, I have left child, 20, 40, 30, and then 60, and ultimately 50. Okay? Are you with me? Okay? Some of you are better in recursion, then you follow me. If some of you are not good in recursion, then you will notice some problem in that. Okay? 50, 30, yeah. 20, 40, 30, 60, 50, yeah. 30, 40, 30, 50, 60, 50. Okay. I even need to check myself. Any questions? Yeah.
I just noticed that all of the three are depths first. Why don't we use breadth first?
Because it's, the siblings do not have links. Now, here I've raised a good point. You notice, as a human, you may think that the best way is 50, 30, 60, 20, 40. You say problem solved, right? Why do I never do that now? There's a difference. We call it breadth first. That means you go from level to level. But you look at this. If you look at the data structure, you notice an edge between parent and child, right? And you look at the C source code. You see there's a left and right, right? So you connect to your child. Is there any pointer to your sibling? No. So for this data structure, finding your data sibling is very hard. Okay? Imagine, now again, you always need to use a concept of this tree has 1 million nodes. Okay? And when you have 1 million nodes, to find all your siblings will be very, very long. So it's not that it's not possible, but it's not a normal way to traverse because it's very slow. So a binary tree is not a good way to implement that kind of tree. You get my idea?
But I remember in some point I am asked to use EF.
Yes. So you need to use other, or you need to make modification to that. Yeah. You're right. Okay. There is a need. Okay. This free traversal at this moment, you don't understand why we choose this free one. Okay. But then, of course, you can still do it now. If you want to do the ordering of 50, 30, 60, 20, 40, what data structure will you need to use? Oh, silence. Some of you want to get an A, right? This is a kind of question that what data structure we need to use as a helper? Okay, I give you more specific. You need a helper. Well? Yeah? What you need? What do you say you need? Okay, now, if in this case you can imagine you have a node, you process yourself, you have children. You usually use a stack. You push all the children to the stack. And then, after you process all the children, you push the grandchildren in another stack. Okay. Now that is one way of doing that. Of course, you say you can use a list. Okay. But then ultimately, you realize that you need a binary tree and an extra stack to do the operation of it. That is expensive, right? Imagine it's 1 million. Okay, so it's expensive. Good questions anyway. Any question about the traversal? Now the key point out here is that when I ask you to do a traversal, you don't even know which traversal to use. That's the reason we say binary tree is complicated. Okay? What traversal, you ask? Which one should use? You don't know. Okay? That's why you don't know. Now, for insert, it's the same. Say, now I have a tree. I insert. Every time I insert to the tree, I put it as a left child. Ultimately, your tree always looks like this. It becomes a linked list. Have I done anything wrong? I haven't done anything wrong, right? You say insert into the tree. I just insert to the tree. What's wrong? But you know that it's wrong, right? What's wrong? Okay. Obviously, I invented a binary tree for a reason, right? So why am I interested? Why when I insert, you say something is wrong? Again, this is ambiguous. Okay. Now, we have a word for that. Have you seen any tree like that in real life? Well, in a tree, we want it to be balanced, right? For some reason. So we also have the same concept in binary tree. We say the tree here is called imbalanced tree, and it is degenerated into a list. Okay. Now, you have seen this word before. When we say you have a hash table, and all these collide, we call it degenerate into the list. So here it's the same. It degenerated into the list. Okay. Now our intuition will suggest that we don't want it to degenerate into a list. We'll see that later. Why? Okay. But you know that it's complicated, right? In a linked list, you just add to the end, right? Or insert somewhere. No ambiguity. Now even for delete, it's a hassle. Look at this. Now I want to delete the root. What can I do? All of them are failing, right? I delete the root. I like to promote the grandchildren. Okay, and it becomes a tree like that. Okay, no, I say I delete the root and I promote the immediate children. Okay, now it becomes like that. Okay, if I delete the root, now I know I want to promote the right child. Okay, it becomes like that. Okay, there are actually many ways for you to do that. Okay, there's only 3 ways. Now, all of these cases are fairly binary trees, right? But the shape of the tree is different. Okay, all of them still in depth of 3, but actually I can, do some trick and make sure it doesn't. Okay, and the number of leaf nodes will be different. Okay, who will be roots will be different. Okay, again, when I delete, I have so many choices. Okay. So what's up with this data structure? Why whenever we do any operation, something is ambiguous? Now, the reason is that it will require you to have an application context. This is your first data structure that happens this way. Now, I have highlighted here. Binary tree is not often used purely to its structure. It is in fact a very important data structure because binary tree is used extensively in searching and sorting. Whenever a tree, I'm actually sorting people into branches, right? Say you are a girl, you see a lot of boys, then you sort them, friends, potential dates.